Okay, class, I want to introduce the idea here of vectors. Now, a vector consists of two things, magnitude and direction. That's really all we care about. Okay, the magnitude is designated by the length and the direction by the direction. So we know about a line that goes infinitely in both directions. We know about a line segment between 2 points. A vector is like a directed line segment that just starts in the point and shoots off in one direction. And then, so we can think of a vector a lot like we would a directed line segment, except all that we really care about in a vector is magnitude and direction. Okay, and by that we mean that a vector is considered equal to another if its magnitude and direction are identical. It doesn't really matter where the point starts. So this starts at a point P and ends at a point Q, but it's the identical vector to this one that starts at R and S. Why? Because it's got the same length, which represents the magnitude, and they both go in the same direction. So if we thought of a slope of a line, it would be rise over run would be 3/4 for all of these. And they only take up 4/3 square, so these are identical. So we can just say that a vector is equal to another, and we identify a vector as a directed line segment, PQ in this case, but it's identical if we called this one here that goes from T to U, if we called it W, then B and W are equal. Okay, so all of these are equal vectors. Okay, and then if we think about what we mean by a zero vector, so this is a vector that has no direction and it's got no magnitude. So essentially it's nothing, and we'll refer to that as a zero vector. Okay, now let's talk about what it means to add vectors. So if we take the sum of two vectors v and w, we're going to add them. What that means is that we're going to take the vector v and place it somewhere, and it's got a magnitude and a direction, and then at the very end of the arrow here, where its magnitude stops, we're going to place the vector w, and that's going to take us in a new direction for a different, potentially different magnitude. And whatever results, the start point of the addition and the end point are the new resulting vector. So we combine v and w in this way to make a vector we could call v plus w. Now, there is a commutative relationship. So if I decided to start with w and then add v, so let's look at this example here. So if I start with w, w looks like this. It goes in that direction for that distance, magnitude. And then when I place v, wherever else I find it, if I place it at begin at the end of w, it takes me here. And it turns out that if we took this v, notice this v down here that's blue, has the same magnitude and direction as this v. So if we start with that instead and then tack w onto that, it's always going to take us to that same point, and it's always going to create the same vector, whether we call it w plus v or v plus w. This resulting vector is always the same, and we call that the commutative property. And if we remember the associative property, this is the one that says if I add in a different order, in other words, if I do my parentheses first and then take u plus whatever the result of v plus w is, I get the same result if I take the result of u plus v and then add w. So it's a little more busy looking in here to demonstrate it, but let's just do this. We're going to start with the u, and then if we find v plus w and then tack it onto the u, it lands us here. On the other side, if we shift those parentheses and start with the u plus v, and then we take and add to that the w, we're going to get the same result, which is this red line is my new vector that is the result of the sum of these three vectors using the associative property. Okay, so here's some more ideas to build our intuition about the vectors. If I take some vector v and add to it the zero vector, or I take 0 and add it to the vector v, I didn't change the vector v at all. Okay, because remember, zero vector is nothing. On the other hand, if I take the v vector and add to it its opposite, then the result is nothing because the result has no magnitude and no direction. Okay, we started with V and then went negative V. Takes us right back to a location where we started with no magnitude or direction. Okay, and then what we mean by a subtraction of vectors is if we take a vector V and essentially we add its opposite. So W is actually pointing out here, so this would be W, but negative W would be the very same magnitude in the opposite direction. So that would represent a V minus W. And since we started at this point here, and by taking V, subtracting W, it led us to this point here, the result of V minus W is this vector right here. Okay, let's talk about a scalar multiple and how does that work with a vector. So if we call this alpha a scalar and we scale some vector V by taking that scalar times alpha, and if it's greater than 0, it's just going to be alpha times the magnitude it once was. So here, if I take a vector V has a magnitude and I double that magnitude, so I take 2 times V, it's just going to maintain the same direction but have a magnitude that's twice as the original. And if I take a negative number, so alpha is less than 0, then it's still going to have the magnitude that's the absolute value of that alpha. So if I took a negative 2, for example, it would take me in this direction, but the same distance or magnitude as I'm going in this direction. So we see that with the negative 1v. It just takes this vector v and its original magnitude of 1, but takes it in the opposite direction. So it's still got a magnitude of 1, but the negative 1 indicates the new direction. So here's some examples of scalars that have a significant result. So if I take 0 times a vector, I get the 0 vector. If I take the scalar of 1 times the vector, I haven't changed the vector. It's identical. If I take negative 1 times the vector, it would be the same as negative b. That's pretty obvious. If I take the sum of 2 scalars and multiply it by the vector, the distributive property is going to work here in the sense that I can take alpha times v plus beta times b. If I take some scalar times the sum of 2 vectors, which is different, I can also distribute that and get the same result. And since multiplication is commutative, it doesn't matter if I multiply in different orders. So these are just some of the basic properties that help us understand how vectors do. Okay, so let's do an example here and have a little practice at operating on vectors. So we've got the vectors defined in this space over here in our figure 49. These are the materials that we're working with. And this part A says I want you to take the vector v and subtract the vector w. Okay, so here's the vector v, so I'm going to pull that off and start with v. And then if we subtract w, we're going to take w, which originally goes like this, but we're going to take its opposite direction. So it's still got the same magnitude, but instead of dropping down below here, it's going to push us back up here. So what they asked for was the result of v minus w. So the answer then would be this vector here in black, because that starts with v, and at the end of v it takes the opposite of w, and that lands at this point. So we've defined v minus w. Okay, so same thing is going to take place for each of these. All right, for this next one, we're supposed to get 2v plus 3w. So the first thing we got to do is take this v out here and take its direction and its magnitude and double its magnitude. So that 2v is going to take us up here. And if I were to take 3 of these w's, it would be like 1, 2, 3 w's. So since the starting point for 2v was here, and the result when we take 2v and add 3w takes us here. This is the vector 2v plus 3w, this one here. All right, this one's going to go all over the place. We're going to start with 2 v's. So again, I'm going to take these v's. So this vector is the same as this vector. They're both 2v. But then we're subtracting w, so that takes us not down to the right, but up to the left, the opposite direction. We're not changing u, so we're just going to drop u at the end of this result. And since that took us from our start point to this point, the vector that they asked for is this black one here.